let's talk about decoders as Minterm generators. Minterm generator decoders are always active high. Active high, Minterm generator. And we've seen with the decoder, the active high decoder, that for each one of the inputs, exactly one output is a 1. And we've seen in this example where this decoder, where we have a 3 to 8 decoder, we would know that when the input is the binary 0, 0, 0, which is a decimal 0, that line D0 would generate a 1. For any other input, we know that line D0 generates a 0. Same way, when our binary input would be 0, 0, 1, decimal 1, we know that D1 generates a 1, every other line generates a 0. Very similar then to solving for minterms in the truth table and generating minterms, right? Because we know that these outputs tell us what the input value is. Right? So here, if we have a function of z, y, and x, where z is our most significant bit, x is our least significant bit, is a function of 2, 4, and 5. This tells us then which minterms generate 1s. We know that every other input in the circuit should generate a 0. What we can do is then tie the input lines z, y, and x. So most significant bit, z, gets tied to most significant bit in the decoder, A2. Y gets tied to A1. Least significant bit, x, gets tied to A0, right? So we maintain that same bit order. And what we do then is we tie output line D2 to an OR gate, because if we were to write this function as a sum of products function, we would take minterm 2, we would OR it with minterm 4, and OR it with minterm 5. So all we need to do is then we put an OR gate, because we have a 3-input OR gate, because we have 3 minterms that need to flow into the OR gate. We tie D2, D4, and D5 to the circuit to generate F, because we know that we'll only ever have one of these inputs at a time. So whenever we have minterm 2 on here, that will generate a 1 here, 0's here, but we know 1 ORed with 0 generates the 1. Whenever our input is a 4, well, line D4 will be high, the others will be low, but we know that ORing them together will produce a 1. Same way when our input is a 5, a 1, 0, 1. Right? D5 will be high, the others will be 0, but ORed together, that will generate a 1. If we have any other input on this circuit, right, we know that these lines will all be 0. So if our input is a 0, a 1, a 3, a 6, or a 7, all of these lines will be 0s. The output of the circuit will be a 0. Right? So this is how we use a decoder to generate as a minterm generator and to implement a function like this. Right? So we use active high decoders to implement sum of products because they're minterm generators, and minterms we use in sum of products form. So active high decoders are minterm generators. We could also then create an adder from a decoder. So if this is the full adder truth table, right, we're going to add 3 input bits, x, y, and z. Sometimes we would have cin, x, and y here. Doesn't matter so much what we call them, right? We know for a full adder we have 3 inputs. When we add them together, 0 plus 0 plus 0 is they're going to generate 2 outputs, a carry out and a sum. All right, so here's your full adder truth table. If you don't remember that, revisit the lecture on full adders to see how to generate this. And what we can simply say then, right, is the sum of x, y, and z. Well, we have 1s in these locations, is the summation of 1, 2, 4, and 7. Carry is the sum of 3, 5, 6, and 7. Right? We use a minterm generator, an active high decoder. The active high decoder here, we tie the inputs x, y, and z here together. So in this decoder, I just have a bus representing the 3 data lines, right? You would tie into the bus, x would be tied to line, basically your A2, your A1, A0 is what we call these in the previous truth table. You tie these into this input data line. Remember, this is a minterm generator. Then for the sum, right, we said the sum is 1, 2, 4, and 7. we need minterms 1, 2, 4, and 7. So we tie those into an OR gate because remember with minterms, we OR these together. We OR minterm 1, ORed with minterm 2, ORed with minterm 4, ORed with minterm 7. Similarly here, we need another OR gate with 4 inputs for these 4 minterms, 3, 5, 6, and 7. So here's our carry, 3, 5, 6, and 7 tie into here. There's our carry. Here's our sum. So we didn't even have to do Boolean algebra when we used the decoder, right? We simply had to indicate where our ones were. Go ahead and use an active high. This has to be an active high decoder, right, to uniquely generate the ones. And this is how we implement then a full adder with an active high decoder, right? Remember, active high decoder, Minterm generator. You need the OR gates out here because you OR the minterms together. You can think of this as replacing that lower level set of AND gates. Remember, in some of products, it's an AND OR circuit. This gets rid of that level of AND gates. We just have our OR gates out here because this tells us what the minterm is. So this is a fairly easy circuit. Once you remember that this is a minterm generator, your gates go out here on the right. Sum of products, the upper level gate is an OR gate. You tie these to the lines. Boom, no Boolean algebra. All right. We can also then use decoders as Maxterm generators. These will be active low. So Maxterms, remember Maxterms you solve for 0. So it makes sense then that you have an active low decoder. Right? Minterms we solve for 1s. It makes sense that we have an active high decoder because active high decoders uniquely generate 1s. Active low decoders are the opposite. They uniquely generate 0s. Right? So an active low, 1 input to 2 output decoder. So here's our 1 input A. Right? It's going to uniquely generate 0s. It's going to tell us whenever what Maxterm value is on the line. Right? When A is a 0, D0 is a 0. Every other output will be a 1. When A is a 1, D1 will be a 0. Every other output will be a 1. We can then have a 2 input to 4 output active low decoder. So active low, right, we're replacing then again the 1s with 0. So D0 is a 0 whenever our input is a 0. D1 is a 0 whenever our input is a 1. D2 is a 0 whenever our input is a 2. So 1, 0, binary 1, 0 is decimal 2. Binary 1, 1 is decimal 3. D3 is a 0 whenever our input's a 0. So again, this is just decoding our inputs, but active low will produce a 0 when we have those inputs, and will produce 1s everywhere else. That's why we call these Maxterm generators, because if we go ahead and solve D0, right, for the 0, we generate then this sum term or this max term, right? These are all max terms. So this is how we would then derive our circuit equations for an active low decoder, right? We could then, same way we did with the active high, we could use our OR gates, right, to generate these individual circuits. We could write Verilog for this. We haven't done that in this case, right? We did all of that for the active high. What we want to do is knowing then that these uniquely generate 0s, that an active low decoder is a Maxterm generator, then we can use these decoders to implement circuits. So remember, active low decoders are sometimes called Maxterm generators. They output exactly 1, 0 for each input. And so now if we had our function of z, y, and x is a product of 1, 4, and 7, well, if we tie the output lines 1, 4, and 7 to an AND gate, because remember, product of sums, well, the sums are the max terms, and you AND the max terms together. That's why we have an AND gate out here. So we're going to AND max term 1 with max term 4 with max term 7. Right? We tie the lines, the inputs z, y, and x, so z goes to the most significant bit, y to the middle, x to the least significant bit. And we can simply implement that circuit, solving for 0s. So Maxterm generators are active low decoders. Active low decoders produce a unique set of zeros. They're just the opposite of active high. All right, and so that's it then for Maxterm and Minterm generators. That's it for this portion of lecture on decoders. Right, you'll do some homework problems with that.